Welcome to our business track of the Data Science Salon YouTube channel. This is a presentation by Anusa Trivedi, Senior Data Scientist Lead at AI for Good at Microsoft. In this session, Anusa dives into how the actions of AI are the result of human inputs going into programming. She shares how an AI's bias is not its own, but the human bias with which it's been programmed, and emphasizes the choice of the right metric and the type of data used for testing and training to avoid such bias. She discusses the need to understand the dependence between the data used and the models employed and optimize only areas that matter, and how to focus on feature engineering while being thoughtful about the ethics of ML applications. Please enjoy.
I am a data scientist in Microsoft Research. So this is an AI for Good research lab, which started just last year. We all hear about AI for Good a lot, but there are some specific verticals we are targeting. AI for Earth, you might, if you are from around this area, you might have heard a lot about it. So AI for Earth is one of the verticals that we work with. AI for Health is one of the verticals that we work on. AI for Humanitarian Actions and Philanthropies is another vertical, and AI for Accessibility. So we majorly target these four verticals. There is a team of data scientists that work with me. They're my colleagues, and they come with like various backgrounds from economics, from philosophy, from computer science, from statistics. And we try to use very similar algorithms, but we need to refine them for applying into very vertical specific problems. My talk today is on the AI knobs, specifically what are the things that we keep in mind when we are adjusting these algorithms for very specific fields. I mean, there are some generic rules you need to use when you are trying to move one set of algorithms to another one, and that applies across all verticals. Okay, so the first point is learning. Right? You need to keep in mind that you are learning always. So I usually like to break it up, learning, into 3 points: representation, evaluation, optimization of algorithms. Representation is the way in which you are trying to choose your classifier. You're trying to represent your problems, and they're very different when you're targeting different types of data coming from different verticals. And you need to set your hypothesis space really good to make your learner more and more effective. If the classifier is not in the hypothesis space, it cannot be learned. For example, we use deep neural networks for languages all the time. There are multiple different tasks that we address. For example, one of my work was with Jimmy Carter Center, an NGO who works in the Syria war mapping zone. One thing they were trying to figure out was, how do we figure out what are the causes or the events that's causing still a number of deaths in certain specific areas? Is it like a strategic development from the government which is causing this? So that like UN, and they produce weekly reports to UN, and so that you can take the needed steps for such interventions in such areas. So very sensitive project, very different type of data set, because as you might imagine, they're not even allowed to share this news or this kind of, so we need to go scrape the data as soon as possible. Somebody tweets or something like that. So instantaneous collection of data, how you curate it, how you try to bring it in a format, and without any labeling, try to classify your events. So it's a super, super difficult problem, but we used very generic neural networks for that space. And we tried to use different types of labeling techniques, and maybe some other day you'll hear me talk about it. It just got accepted as a paper. So, but the thing is, there are different problem spaces, and these are some neural networks which we use for our retail space, for trying to figure out how you can influence buyers. So what are the events that cause that actually triggers buyers to buy more of your product? So it's very similar. It's just that how you're defining your hypothesis space to try to solve the problem at hand. Evaluation, very much needed. You need to distinguish good classifiers from bad one. You need to figure out that you're not overfitting on your data set, because some of the verticals that we work with, just the example that I gave you, there is not a ton of data to work with. So if you try to start applying some neural network techniques, it might start to overfit, and you need to figure out whether if you are actually doing a good job evaluating it on out-of-sample data sets. Optimization, definitely another one that you need to keep in mind when you are modifying your algorithms from one problem to the other. So there are some generic optimizers that come off the shelf, but you might end up defining your own optimizers. For example, for the same algorithm I'm talking about, when I apply it to microbiomes in genetic for AI for health, to figure out what are the microbiomes affecting one particular disease, I need to write my own optimizers because it does not know my own vocabulary, because it's a very, very genetic specific vocabulary. So it might be something that you need to create for your own. But the same basic neural network, working with a custom optimizer might give you good results. So it's generalization that counts. You need to keep in mind, you need to make your model as generic as possible. There is a trend whenever we teach in classes, it's always comes down to that, where like whenever I say, oh, you take your data set, you do a 70, 20, 10 split for your training, validation, and testing, and then voila, you have your test data set and you have worked out and it's like 93% accurate, this much high accuracy, specificity, sensitivity, this one. Great, that's good for papers. But when you actually go out to solve the problem with NGOs, an actual real life thing, and you're building a product out of it, you need to keep in mind, how can you generalize more so that it works more and more on your out-of-sample data sets? One of the problem, I'll describe another project that I'm working with at NOAA, National Oceanographic Center, and they were trying to classify fish species, right? Species of fish, so that they can control how climate change is affecting population of certain species to disappear. And it's very essential to maintain that balance, otherwise the whole ocean ecology around the Puget Sound area is actually getting disturbed. So how do we do that? But they didn't have as much of data to work on that problem. So trying to scope it down to generic fish detectors, helping them, one person is sitting, for NOAA, one person is sitting all day going through slow frame rate videos trying to recognize what fish is where, right? That's not efficient. That's not how you can solve this type of problems. So if we can develop some generic fish detectors for them, right, and help in the labeling process, and then you can go and target the classification and trying the counting of the fishes, more specific problems. Try to generalize your problem as much as possible as the first step, and then you can go down to the more specifics. Training and testing data. As I already said, you need to be very sure what are your if you're developing a binary classifier, what are your positive, negative distances? It's a non-trivial task. Now, let's give you an example from the Xbox team, right? Is this a positive or a negative example, right? User plays a game to completion and rates with 1 star, okay? Maybe that's a negative. User plays the same game again, but maybe because you couldn't find anything else, right? But you do not know the reason. User abandons the game after 5 minutes or 15 minutes or an hour. Is that a negative, or is there something that she needed to do urgently? You have no feedback on that. User adds some games to her list but never plays it. Maybe she didn't find time, like I never do with my kid. So what I'm trying to say is there are lots of unknowns when you're trying to develop labels for your data sets. Try to take as much of external factors into consideration when you're trying to do the data engineering or the data processing of your data, even before when you start testing your algorithms. Other training data issues is time traveling. Especially if you're working in a user-related environment where you are dependent on your user feedback for your labels, it's always mostly after that event has happened. For example, your rating of a game is pretty good prediction that you like playing that game, but it almost comes after you have played the game. So here is a concept of online and offline. So there is an online labeling, offline labeling, there's an online testing, offline testing. So there are like different types of concepts when it comes to training data. So you need to keep that in mind when you're moving one of your algorithms to another scenario, and how you need to modify your data in that sense. Overfitting has many phases. So everyone in machine learning, whoever are accustomed to this, knows a lot about overfitting, how we should overcome them, but they come in many forms. Especially, we can divide them up broadly as bias and variance. Bias is a learner's tendency to consistently learn the same wrong thing. You're not actually taking the signal into account. You are going on trying on some wrong assumptions. Variance is the tendency to learn random things irrespective of the real signal. For example, let's take if you are trying to develop an algorithm for your hospital inventory, right? And you get different types of patient information. How many number of days when was the patient admitted? What was the illness? How many number of days the patient was there? And maybe you're trying to optimize for the number of beds so that you can admit more and more patients in. So now in that case, there is a sense of bias which can come in. Oh, if it's like more of a surgery, the person might need more number of days, the beds. So you need to keep that kind of thing in mind. There might be some investigative thing going on, and you might need to allocate the patient more number of days in the bed. Variance is you're not getting the signal correctly. For example, you're not looking at your past data as well as your trends that your signal is giving. For example, you are trying to take the patient's all the vital stats and everything into account when you're developing a model. That's not the right way. That's not what you're optimizing for, right? So there is a really bad low correlation between the problem at hand and the features that you're trying to use. Always use features which are highly correlated to your problem at hand. And one of the ways you can do it is feature ranking, right? Very, very basic thing that you can do to handle that kind of a thing. So fighting overfitting, the very basic thing that you can do is cross-validation. That can definitely combat a little bit with overfitting. For example, by using it to choose the best size of the decision tree that you want to learn. You might want to learn a decision tree for something, but you might need to figure out what are the levels that you want to go into, what are the features of the decision tree that you want to consider. If we use too many parameter choices, it can start to overfit on your specific choices. Besides the cross-validation, there are some other methods. For example, the most popular thing is adding regularization. We do that all the time in neural networks when you try to evaluate a function. Another option is to perform a statistical significance test like a chi-square test, right? Before you're trying to add a new structure to your evaluation phase. These techniques are particularly useful when the data is scarce, which is mostly the case in applied research. The curse of dimensionality, right? Intuition fails in high dimensions. Imagine you're working with a very, very large corpus, right? And you're trying to generate automatic tags for the corpus. For example, it's a corpus of big blogs. And whenever you go to read blogs, you see such keywords, right, in the below. So there is like, it's sports related, AI in sports. So for example, you will have AI, sports, this kind of tags when you are trying to provide keywords for such blogs. But the problem is they are highly correlated to the content of the blog. So how do you try to figure out, because whenever you try to do something like SVM, 2D matrix factorization, it's a huge, blows out of proportion. One, you have two vectors now. One is your keywords. One is the content of all your big corpus of the blogs. Now that is a huge matrix that you have. And this one is a really small one. So how do you try to optimize them? Right? Just a linear PCA, linear dimension, will make you lose the correlation to the keywords that you have. So something like canonical correlation regression, right? For example, CCA might be better. So trying to figure out your problem space, what are the correlations that you need to take care of, and how you try to combine two vectors. It's a simple concatenation, and then applying CCA instead of PCA could be one thing that you can go for. Naively, one might think that gathering more features never hurts, but it's always seen as the opposite case. In fact, the benefits might be outweighed by the curse of dimensionality. So be very sure when you're trying to choose features for your problem. Is more data better or better models better, right? There is always a debate on it. So should I take a simple model and apply more data to it? Or should I, if I want to work with less data, should I better make my model more complex, right? So this is a book I recommend, The Unreasonable Effectiveness of Data, and they talk about, this is written by Google authors, and they talk about Google does not have the better algorithms, only more data, right? And they actually acknowledge that. But does that mean that more data is always better? Not always. I mean, it's more data is definitely helpful, but especially in applied research, where the type of problems that I was talking about, it's not possible to get data, and data alone is not enough. This seems like rather depressing news, but luckily the functions we learn in the real world are not drawn uniformly from the set of all mathematically possible functions. There are some functions that you might define to define yourself. In fact, very general assumptions like smoothness, similar examples, having similar classes, limited dependencies, or limited complexity are often enough to do well. For example, I was working on an automatic detection of diabetic retinopathy. Diabetic retinopathy is a disease which actually affects 80% of people in US having diabetes. It's an incredible number of time, and it results in complete vision loss if it's not detected at an early stage. So what do you do there? I mean, the data is not readily available. It's very, very race specific. So if you are able to gather some data from maybe, say, India, China, it does not work. It does not meet the FDA approval process because it does not work very on Caucasian population. So what do we do? There are certain techniques that you can actually take to make your data more generic. For example, background removal is one technique that we all the time, where you're not overfitting at all on the background, but you're actually focusing on just the problem is vasculature of the eyes, which is just the vessel structure of the eye. When you remove the fundus scan image from the background, gives you clear, strong indication of how cardiovascular diseases are related to your eye disease. Okay, so what you kind to do is try to figure out what your problem at hand is. Try to take different types of very similar techniques. For example, smooth your data, apply more noise to your data. Try to do image similarity, right? Try to see how much racially different your pigmentation is from a brown person to a Caucasian person, right? So you try to do all of these things and try to generalize your data by introducing more color, more pigmentation, maybe more blurring, and adding more noise would help in actually generalizing your data for different problem spaces. Like deduction, induction is a knowledge lever. It turns small amount of input knowledge to a large amount of output knowledge. So the way, if you know your problem space and you can figure out the actual ways to leverage your data at hand, you can definitely work with it. You do not need big data for everything. We always hear that. We do not need it. Today we all have access to big data, but not everybody needs it. It's good to have it, but not everybody is as fortunate to have tons of user data. Many times doing smart, for example, stratification of your data, right? Sampling can produce a good or even better results for using all. That way you also make sure you're not overfitting if you're using a less complex model, right? Feature engineering, right? Feature engineering always is the key to success of your machine learning algorithms, and we all know that. At the end of the day, some machine learning projects succeed and some fail. So where do we go? Where have we gone wrong, right? So maybe we did not choose the feature. Coming back to what I was saying, you need to be very sure about the variance. What is the real signal? What features are giving you actual signal for your problem? If you have many independent features that each correlate well with each other, obviously you have a great feature space to train your algorithm on. But if the class is very complex and function of the features, then you might not be able to learn it as well, right? That at that point of time, you might need to figure out, okay, how do I do some feature ranking? How do I do some other correlation mapping and pre-process, maybe apply some other algorithm to my data and try to do feature engineering in that way. Because it's a feature engineering also is difficult because it's very, very domain specific, while the learners can be very, very general purpose. Learn many models, just not one. I mean, we all know, whoever work in the research space, you have to give your baseline, then 3 or 4 different previous research, and then you have to, whenever you're proposing algorithm, you have to, do the comparison, this chart, that chart, everybody knows that. But how much do we abide by that when we are actually producing a model in production? In production, it's also needed, if not more, right? Instead of selecting the base variation found, we combine many variations, and the results are often much better, or even if we have to put a little bit of extra effort. Creating better models work, for example, ensemble techniques like bagging, boosting, stacking. In bagging, we simply generate random variations of the training set by sampling, learning a classifier on each, and combine the results at the end. In boosting, we have training examples have some weights that you have tried to apply on, and these are varied so that each classifier focuses on the examples of the previous one, whether it has learned wrong or not. In stacking, the output of one layer is going as an input to the other layer, right? So basically, you're trying to learn in steps and trying to come to a decision about whether your model have learned better in the other step or not. There are various techniques to examine. It's more and more the ensemble size it's going towards a more bigger size. Working with deep neural networks, right? I cannot skip that because everybody is working with deep neural networks nowadays. I'm just keeping a tab on my time so that I'm not taking other people's time. So as we see, machine learning have always been there and it's still widely used, but there are some problems where deep learning is starting to do a much more better, especially since 2012, where we were able to start, using GPUs, come back to the computation power, solve the problem of data and everything. The trick is hyperparameter optimization. We need optimization by choosing the right metric. Obviously, the suggestion is do not use a grid search. Try to explore more and more Bayesian optimization. There are lots of optimization packages nowadays which uses Bayesian or Gaussian process to optimize your feature space, so you can actually do it. So let's tune everything tunable. Okay. As I said again, understand the problem where neural network is needed. If it's not needed, do not use it, right? Because it's harder to justify your use of neural network, and we should not just be using it because it just sounds cool. Or I have a ton of compute power. If traditional ML algorithm solves your problem, that's the best way to go about doing it, because that's less of a black box technique, and you actually know what are the knobs that you have turned it, so you have more control on the model. There are different types of deep learning problems. For example, we know deep learning very well on images, but there are 4 different types of image learning problem, and you need to figure out what is that you're trying to figure out. For example, I'm working with one NGO who is trying to figure out malnutrition in India. And what they have done is they have gone and collected tons of pictures of kids, and not only just RGB pictures, point cloud data. Right? And at this point of time, like, okay, you have this ton of data, but I do not know what you want. So for malnutrition, if you guys are not sure, there is wasting, stunting, and I think MUAC, middle upper arm circumference, that are the 3 indicators. But if you're actually trying to figure out, okay, maybe for MUAC I need a segmentation, but then I need a 360-degree view. But for height, I might need a classification. For weight, I do not know how to apply AI. So because it's not possible only from images, I might be just producing some wrong signals. So it's very essential to figure out what are the specific problems that you're trying to predict, even within a broad problem, and you need to know what are the things that you want to target your deep learning with. So deep learning tasks and goals are text analytics, text translation, different types of tasks related to text. And if you want to work on all different tasks, the first and foremost thing that you need to do is build your own AI toolbox. There are tons available, but as a data scientist, you need to build up your own toolbox, right? You need to choose the concept, the techniques, the infrastructure that you want to work on. There are some common deep learning models. You might actually use any of them to solve most of the problems that I talked about. There are some deep learning libraries. You can decide which one you like. And stack up on the toolbox. There is a ton of open source resources available. That's how I go. I create a VM, I stack everything up, I try to create multiple Python virtual environments, and I try to keep the baseline same for almost all the problems. That gives me a platform to compare my own models to one another and how to figure out what are the things I need to change if I'm trying to apply the same algorithm from one problem space to another. Obviously, take advantage of the infrastructure, distributed training architecture. There are many ways in which you can do it. Data parallelism is actually where you actually are dividing up the data. If you have very low memory size. Model parallelism, you have multiple GPUs and you can run different versions of the model for hyperparameter optimization, anything else. And the last thing is bias. Bias in is always bias out. So building better AI models always have to deal with bias, right? Make sure that you're not introducing them when you're actually defining your problem space. So what is bias? Whatever causes an unfair action or representation that often leads to harm rather than betterment. So how does this relate to algorithms? Whatever causes an algorithm to produce unfair actions or representations, we as human beings, each and every one of us are biased unwillingly, right? So many decisions along the way to develop a computer system comes from humans and the data they create to enter the process. So biases that exist in the workplace, the community, or the culture can easily enter into the process and can be codified in programs and models. Some few examples, right? Facial recognition systems that don't see non-white faces, right? We have all seen into it because of less availability of such data or standard research papers or standard research data sets which have used or introduced the very initial baseline models. We have now developed some systems which don't see non-white faces. So racial bias, resume screening systems that filter out women. Gender bias, right? We have seen, definitely there have been stories out that there are automated grading systems, hire systems, which are failing because of this, and companies are taking steps to actually stop that. There are algorithmic bias coming out. So machine learning isn't magic. There's a lot of human engineering. So we want to create or collect training data, decide what features goes in, decide what you want to predict or classify, and bias could be introduced in any of these points. So how does bias affect training data? There are I divide it usually up into two broad sections: historical bias and representational bias. So let's look at what historical bias is. It's a data capture bias and unfairness that existed in the society. Marginalized communities are often over-politicized. For example, if I'm looking at some very rigorous caste system from India, I'm taking the example because I'm from there. So it's always over-politicized because you want to get some type of grant. You want to get some monetary involvement and more searches, arrests that leads to prediction that there is more signal on that thing. Maybe there is not, but that's how the bias is introduced in the data. Women are not well represented in computing, so there's little data about hiring success that leads to predictions to keep doing more in the same, right? What if we add more training data? Adding more training data just gives you more historical bias, right? So it does not get rid of it. Representational bias. It's a sample in training data is skewed and not representative of the entire possible population. That's why sample is essential in statistics. You have to make sure that you're sampling it correctly, you're stratifying your data correctly if you're trying to produce some unbiased algorithms. Facial recognition system does not identify correctly. Fake profile detector trained on name databases made up the first and last names. Other names are more likely considered to be fake. So if we are careful and add more representative data, it might help. It's basically targeting more smaller classes. Using proxies as conclusions. We often want to predict outcomes that we can't specifically measure. For example, will a student succeed in college? Will a job candidate be a more productive employee? Does a search result satisfy a user query? For example, these are correlations, but these are not causation. So we always use interchangeably causation and correlation. So we need to figure out what are the signals I'm getting from this, and that's not the causation of this thing, right? We always take proxies as conclusions. So most of the time proxies come from socioeconomic status, race, gender, immigration status. So if you're actually trying to say that is the causation, that introduces bias. Why should we care, right? Everything is working quite well with a little bit of glitches. Why should we care? It's a feedback loop. If we start actually training models on bias data set, we are actually creating more and more historical data based on bias. So we are actually propagating a whole society which is biased. So there are different kinds of harm. The resources are allocated based on algorithms, and the representation are reinforced and amplified with this biased algorithms. What can we do about it? Report it. Whenever you see it, there is an actually algorithm-ingestic league where you can go and report bias. Share it, tweet it, actually give out everything so that companies are always looking out for it, and they are happy to get your feedback. So this is what we can do as a community to actually make sure there's no bias coming into our algorithms. And thank you. That's the end of my talk.
That was a presentation by Anusa Trivedi, Senior Data Scientist Lead at AI for Good at Microsoft, on how actions of AI are the result of the human input going into its programming. She shared her insights on the need to understand the dependence between the data used in the models employed and optimize only areas that truly matter. She shares how to focus on feature engineering while being thoughtful about the ethics of machine learning applications. If you enjoyed this talk, please subscribe to our channel below.